Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So good afternoon, everyone. Thanks for coming for this final intern talk. Thank you for those who are watching us online. Today we're going to hear the results from an intern project called Ultrasound-Based Gesture Recognition, which was done by Amit Das, who is a PhD candidate in University of Illinois Urbana-Champaign. And without further ado, Amit, you have the floor.
Okay. Thank you, Ivan, for the introduction. So the title of the project is Ultrasound-Based Gesture Recognition, and I was guided by Ivan Tashev throughout this project. So let's get started. So here's a brief outline about the talk. So I'll talk about introduction and then state-of-the-art literature. Then I'll give a general idea and block diagram of what we are doing, followed by feature extraction, and then the types of classifiers that we have used, and then data collection, data set and evaluation parameters, followed by experimental results, and finally conclusions. So introduction. So why do we need gesture recognition, and why do we need ultrasonic gesture recognition? So modern mobile devices are small, and that's why we don't have a keyboard and mouse to use our hands. So instead, we'll use input modalities such as voice and gesture primarily. So examples of such devices today are Kinect and HoloLens, which use the optical based imaging. So the general principle of the gesture recognition is, so we send a transmit beam which is an infrared beam, and then we do some depth image estimation that is pretty much estimating the distance of the target object using the beams. And then finally we do some classification. So for example, it could be maximum likelihood based classification to get an image. So what are the motivation and issues to address? So the issues to address are the following. So active probing. So active probing means the device itself is sending a transmit beam. So active probing with optical infrared beam consumes too much power, and it's prohibitively expensive for mobile devices. So why do we need ultrasound? How does ultrasound help here? So sound is a low energy phenomena, and for recognizing gestures, we always do not need such high precision or a very high resolution image. We could probably get away with recognizing gesture with using a low resolution image. And what are the trade-offs we're looking at? The first one is the wavelength of sound is about 8.5 millimeters, so that's why low resolution. So object dimensions need to be about roughly twice the size of the wavelength to be able to get images of the object. So that's why we cannot try to image objects that are very small dimensions. The next one is the limited speed of sound. So the time that the sound takes to travel and come back as reflections determines how our frame rate is. So because of the limited speed of sound, we have low frame rate in ultrasonic images compared to optical images. I'm sorry. So here's again a quick overview of differences. So ultrasound images devices consume far less power. How they can measure instantaneous velocities directly, as opposed to optical images where they measure velocities through time differentiation. Ultrasound devices are cheaper, there are less data to process, which is also related to because of its low resolution nature as compared to optical image devices. So let's go through some of the state of the art work, recent work that has been done. So the first two are based on optical imaging, and the last three are based on ultrasonic imaging. But however, all the five work listed here, they do depth imaging. So in the first which is the nearest neighbor hand pose estimation. So the optical device tries to capture a infrared IR based image, so 2D images, and then using the 2D images we construct a 3D voxel grid, which is like a 3D pixel or 3D three-dimensional pixels, and then using neural network based classifier we try to estimate hand poses. I'm not sorry, not neural net, but nearest neighbor classifier. We try to estimate hand poses. The problem with this approach is as we know, the nearest neighbor classifiers, they tend to memorize the training examples rather than learn from it. So it's highly prone to problems if the test data slightly differs from the training data. The next one's HMM-based tracking fast-moving objects. So the Kinect camera captures depth images from IR frames at 30 frames per second, and using this raw IR frames, we construct time of flight images, and using those images, we try to build some kind of temporal model to track the evolution of those moving objects. And the next three are more relevant to what we are doing here. So the third one is GMM-based gait and gesture recognition. So the ultrasonic device sends a transmit beam, and then it receives through its microphone array. And because the objects are moving, the spectrogram that we receive are Doppler spectrograms. It changes the frequency of the transmit beams. So based on these Doppler spectrograms, we can typically capture what kind of style of walking or the kind of gesture that the human's performing. So based on these, we can extract capsular features from these Doppler spectrograms, and then we can use GMMs to classify. For example, if there are 10 persons having 10 different walking styles, we construct one GMM per walking style. Similarly for gestures. And so the last two, ultrasonic depth imaging, are primarily work of previous interns in 2013 and 2014. So in ultrasound depth imaging, this was done by Ivan Dokmanic in 2013. So he constructed a microphone array that captures lower resolution images of static objects, and he also used sound source localization to create images, to create ultrasonic images. And the final one is ultrasonic images constructed through Doppler effect. So this was done by Supreet and Hannes. I think this was done in 2015. So here's the brief overview of Ivan Dokmanic's work. So he uses a 8 element transmitter, and here's an 8 element receiver, and using those he captures these images over here. So these are based on time of flight, these are based on intensity, and these are based on sound source localization. And here's a brief an overview of the algorithm, but if you want details, you can follow his ICAST 2014 paper, which I've also listed in the references in the last slide. So coming to our work, so what's the general idea and block diagram of our project? So here's the hardware setup that we use. We directly borrow from Ivan Dokmanic's work. So he used this 8 element microphone array. So we use the same thing, but instead we use only one loudspeaker instead of eight loudspeakers. So this significantly reduces the consumption power by 8 times. And so this is the piezoelectric transducer. This is the 8 element microphone array surrounding it. And then we use a Mo2 A to D and D to A converter to send the pulse and receive the reflected signals. I'll talk about this more in the later sections. So here's a brief overview of the different blocks that you're looking at. So everything in orange, the microphone array and piezo transducers, are the hardware blocks. The yellow ones are all the algorithmic blocks, the software blocks that we worked on. So the idea is that we send a pulse, we send a transmit pulse. It goes through the piezoelectric transducer, and then if there is a a human performs a gesture, we receive the echoes on the microphone array. So this is an 8-element microphone array. So we do beamforming. So and then finally match filtering and compute feature delays and intensity. So what happens is pretty much as soon as we send an echo to the object, we receive the signals, but we try to really scan the object in 17 by 17 in a 17 by 17, like something like a raster scanning 17 by 17 image. So each 17 by 17, so each pixel in that 17 by 17 image is pretty much a look direction of the beamformer. So the beamformer looks at one pixel and then the second pixel and the third pixel and so on, and creates this image. So and the beamforming weights are optimized to focus on those particular pixels at every instant of time. And so once we construct that image, we compute the delay and intensity features, and using those features, we do classification and do the gesture recognition.
How many pixels do you format?
So 17 height and 17 width, so totally 289 pixels.
Is there a size for those pixels? Like in space, how much area do they cover? Does one pixel cover?
So this area is minus 40 to plus 40. So this is the azimuth angle, and the elevation is minus 40 to plus 40. Yeah.
So how do you not get them overlapping? No, how do you not get them overlapping then? How are the pixels not overlapping? If they're 42 degrees,
Yeah.
shouldn't you have overlap between adjacent pixels? What I mean is you have one beam going like this, another beam going like this, and this is one pixel and this is the other pixel. Wouldn't there be an overlap between them?
There could be some overlap because the beam is actually not exactly in that particular angle. So if you're focusing in minus 40, or let's say minus 40 and plus 40. So if this is an image and you're focusing in minus 40 and plus 40, I'll show from the beam shape plots that they have like a lobe that's exactly that could have some deviation from the actual original angle. So the feature extraction stage, it involves 4 stages. So pulse design, beamforming, match filtering, and time of flight and intensity. We'll go through those stages one by one. So pulse design. So this is the transmission part. So what are the requirements for pulse design? So the requirements is that we need to send high transmit power, because sending high transmit power enables us to get strong echoes, and that enables to also build good images. And then high uncorrelatedness of samples. This is because if you want to detect echoes, we want to make sure the echoes are the peaks of the echoes are pretty far apart. They are not smeared across time. So and the way to do that is to have uncorrelatedness across samples. So but these are requirements, but there are some limitations. We don't have, so as in many cases, we don't have infinite amounts of bandwidth or time. So we are limited by bandwidth from 36 hertz to 44 kilohertz, which is the typically the resonance frequency of the piezoelectric transducer, and the time limit is, so we don't have a large amounts of time to send this echo. So the width of the transmit pulse is t pulse, and that should be less than the time of flight, the minimum time of flight. So in simple terms, this means that the last sample that you send out through an echo should be received earlier than the first sample the last sample that you sent out from the transmit beam should be received earlier than the first sample that you receive from the echo. So the minimum time of flight is basically the time that when you're sending a transmit beam, so it travels some distance d and it travels back some distance, the same distance d. So the total travel distance is 2d, which is here, and this is the speed of sound. So the minimum time of flight is 1.7 milliseconds for the nearest object that is 30 centimeters far away. So the minimum time of flight is 1.7 milliseconds. So we are trying to image objects that are not that are 30 centimeters away, and there is also time of flight max, which I'll show later, which is in which case the d min becomes d max, which is 1 meter. So and this is this becomes 5.8 milliseconds. So pretty much we are trying to image objects that are 30 centimeters away from us, at least 30 centimeters away from us, but at the most 1 meter away from us, from the transmit beam. So what's the transmit signal look like? So transmit signal is basically an LFM chirp. It's pretty much a sinusoid sent at every time instant. So here at t is equal to 0, we are sending at 36 kilohertz. And since the frequency increases linearly with time, as at t is equal to t pulse, which is the final sample of the final sample of the LFM chirp, we are sending at 44 kilohertz frequency sinusoid. So the total time limit is so for t pulse is the width of the pulse, which is 1.5 milliseconds. So as I mentioned earlier, this should be less than the minimum time of flight, so which is 1.7 milliseconds, and the bandwidth is 8 kilohertz. So these are the two limitations that we have. So we want to send as much transmit power as possible in these within the t pulse and the bandwidth. And what's the so sending a raw LFM signal causes out of band spectrum. Because it's like putting a time domain box filter in the around the actual signal. So this causes out of band spectrum in the frequency domain. So what we do is we go ahead and try to strip away, remove all the out of band frequency in the out of band spectrum in the frequency domain by putting a rect filter in the frequency domain. And as I said, this is caused the spectrum, out of band spectrum is caused due to sudden transition in time. And once so putting a rect filter in frequency domain will generate a sink in the time domain. So to gradually cut down the sink to make it zeros at the tails, we do a Hamming window. So this is a typical approach for sink interpolation, sink band limited interpolation used in signal processing. So our new the new pulse that we come up with is LFM plus, which is LFM plus some post processing, the rect filter in the frequency domain and the Hamming window in the time domain, and we'll see how it looks like in time and frequency, comparing both the pulses. So this is the actual, on the left column we have the LFM, the raw LFM plots, and the right column we have the LFM plus, which is the post-process LFM plots. So this is simply the time domain signals of LFM and LFM plus. So more interesting is to look at the autocorrelation plot of the LFM chirp. You can see that the autocorrelation extends all the way till more than 200. So this is like 308 and 308. So ideally we want to be able to detect echoes. We want the signal to gradually, once it touches 0, it should stay at 0 and doesn't create additional fluctuations, because if that happens, if it has a long tail, we might mistake it as an echo, as a false echo. So this is a problem with the autocorrelation function of the LFM chirp. But in the LFM plus chirp, you can see the signal actually dies down and gradually dies down and never has any further peaks. So as we know that the faster the signal decays, the more uncorrelated the samples are. So in this case, comparing these two cases, we clearly know that this has more uncorrelatedness than this one, because it has longer tails, this has shorter tails. The ideal case would be to just have one peaky, one Dirac pulse as an autocorrelation, but we typically get that using wideband if you have a white noise. So comparing the LFM and LFM plus in the frequency domain, as I was saying, that it creates a lot of out of band spectrum in case of LFM, but you can see that the spectrum is pretty clean in case of LFM plus, because of the rect filtering that we did earlier in the frequency domain. And so here's a pulse train of both LFM and LFM plus. So on the x-axis we have time, and the y-axis we have the magnitude. I'm sorry, the frequency. The color of the plots is actually the magnitude. So you can see that because of the out of band spectrum, there's a lot of noise across the entire frequency range, whereas the LFM plus train looks pretty clean. And this is pretty much the 8 kilohertz bandwidth that you're talking about, and the width of this pulse is 1.5 milliseconds. So pulse design's done, and now let's move on to beamforming. So beamforming is again a way. So what it does is pretty much receives the receive signal on the 8-element microphone array, and it combines them in a way so that we can get the maximum information out of the signal. So we do time invariant MVDR, which is the minimum variance distortionless response beamformer for an array of M microphones. So assume that S is the target signal, and S is a function of S is the target source located at some angle psi, where psi is a function of phi and theta, which is the azimuth and elevation which determines the position of the source, and D is the capture vector of the microphone array in the direction of psi. So we'll call psi as look direction. So and N is a noise matrix. So we have one noise sample per microphone. So what the beamforming algorithm does is applies a weight to the input signal and the noise, which is a receive signal, and this is the total beamformer output. So ideally, what we want YF to be is just the signal, and try to minimize the noise part over here, and here we try to just get the signal out. So the objective of the beamformer design weights such that the output of the target signal, we get the output of the target signal while also minimizing the noise power. So this can be formed into a constraint optimization problem, where you're trying to minimize the noise power such that the directivity times the capture vector times directivity is just 1. So the optimal weights are given by this equation. So this is the directivity, and CNN is the noise covariance matrix of the 8-element microphone array. So here we assume a diagonal covariance, and know that we do not update CNN for at every chirp or across time. We keep CNN constant. So CNN is measured from we keep CNN the noise power constant. So CNN is a diagonal matrix here. We assume noise is uncorrelated across microphones, and so because CNN is a diagonal and this term doesn't involve any signal, notice there is no S in this equation. So that means we can compute the optimal weights offline. So we don't need to wait for the signal to arrive. We can just compute them offline and apply whenever the signal arrives. So the number of optimal weights are pretty much a function of the number of frequency bins. So F is a frequency bin within the 36 to 44 kilohertz range, and psi is the number of pixels, which is the number of look directions that we spoke about earlier. So this is pretty much 17 by 17. So there are 17 azimuth and 17 elevations. So in total, we split the 36 to 44 kilohertz band into about 115 frequency bins times 289 look directions. So this is how the beam shape looks like. This is in the spatial coordinates, but a better view might be to look at this beam from the top. So that means we lose the elevation, but we can focus on the azimuth. So you can see that the beam looks like this. It has some deviation. So this is actually where the target source is. There can be some deviation from the actual source. So the narrower the deviation, the higher the directivity is. And you can see from this plot that it's pretty much shaped at it's peaking at the 40 kilohertz range, which the 40 kilohertz frequency, which is our desired frequency. And finally, the directivity index. Directivity index is a measure of how directive the beamformer is. So you can see that at the x-axis is the frequency and the y-axis is the directivity index. So at about 40 kilohertz, we are peaking. We are performing the best. So this is typically the resonance frequency of the piezoelectric transducer, and these are the noise gain plot. The red one's ambient, the green one's instrumental, and the red one, the blue one's total. So now, once we are done with beamforming, let's move on to match filtering. So match filtering, why do we do this? So match filtering is optimal in the sense that it can maximize the SNR of the signal, assuming we have wide Gaussian noise. So typically what we do is we assume the impulse response of the match filter is just a flipped version of the actual pulse that we transmitted. So if S of n is the pulse that was transmitted, which in this case is the LFM plus chirp, so we just flip the transmitted signal and convolve it with the beamformer output. So X of n is the beamformer output, S of minus n is the flipped version of the LFM chirp. And what we get out of that is the match filter output. So match filter output, since it maximizes SNR, you can see the effects here. That the red one is the beamformer output without match filtering, and the green one is with the match filtering. You can see that there is a 10 dB increase just by doing match filtering. So this helps us to actually detect the echoes in match filtering. Yes.
Go back one slide.
Yeah.
So it's been a really long while, but isn't this you basically autocorrelating the signal with itself, right?
Yes. So
Pretty much converts the beamformer to receive only one type of signal, which
Yes.
is the one we send.
Yeah, so it's optimal in
In
this
that
case.
sense.
Yes.
And pretty much doesn't apply that noise suppression for other signals.
yes. So match filtering helps to get signals that are in the desired frequency range, but it still doesn't. So we are removing pretty much noise, out of band noise, but it still doesn't get us rid of the echoes that can be present, the false echoes that can be present. So doing a gesture, we want to track this part of the hand. We can get echoes from other places also. So we cannot get rid of those echoes. So that's still a problem here. So now let's compute the delay and intensity features. We try to get rid of false echoes using these features. Let's see how do we do that. So I'll explain time of flight again in a more detailed fashion. So this is the time domain signal of the match filtered output, and this is the big signal here is the actual signal, which is the main signal that we transmitted, and the small one is the received echo. So the distance between the time between those two, the main signal and the echo, is the time of flight, which is simply the delay of echo. And as I was saying earlier, it's pretty much the distance traveled by the signal. It's a measure of so dist is the distance of the target object, is a measure of how early did we receive the echo, and how do we estimate the echo using signal processing techniques. So if S of n is the actual transmitted pulse, which is, you can think of the pulse as this one, and G is the attenuation factor. You can see that the echo is not at the same level as the transmitted pulse, and it's coming at some delay tau, which is the time of flight. So we can pretty much model this as S of n plus G Sn minus tau. And how do we recover? So given that we know Xn but we know nothing about tau, how do we recover tau? So we can do this by finding the peak of cross correlation spectrum. cross correlation in the time domain. Sorry. So this is the cross spectrum. So x of f is the FFT of x of n. S star of f is the complex conjugate of the FFT of s of n. So if you do the inverse Fourier transform of the cross spectrum, you get cross correlation, and if you take the peak of these, so you get a number of taus, a vector of r of taus, and we take the peak of that vector, and the peak is centered, and the peak is, we limit the peak to be within T of min and T of max. So the peak indicates the actual lag that they receive the echo in, and we limit it to T of min and T of max because these are the ranges that we want to depth the image. Okay, so now we know from this tau we can get the so we can get it when you can get 1 tau for each of those 17 by 17 look directions, and we can construct an image out of this tau. But we can also construct an image using the amplitude of the signal. So how do we measure the amplitude of the signal? So we just take, assuming tau occurred at the peak of the pulse. So we take the surrounding samples around tau star and take the L2 norm of the signal, and that gives us the amplitude of the signal. To reject false echoes, we do some thresholding so that if this energy is too low, we simply say no, we don't trust these echoes anymore, and we simply set it to 0. So now that we have, so we measure a L2 norm for every look direction. So we have a tau star and a for every look direction. So now we have a 17 by 17 image for every tau and a. So now let's look at the classifiers. Yeah. Yes.
Given this architecture you just defined, does that mean that if there's nothing in front of the sensor, the output will be a random depth value, because it just be noisy, pick the peak of noise, and then
Yes.
zero intensity, right?
Yes.
So that'll allow you to throw away all those random.
Yeah.
Okay,
Yeah.
thanks. Just
And if for some reason if it's unfortunate that we get an echo early on within the T of min and T of max, and there's high intensity, we just have to pick up the signal. Yeah.
yeah, but it should be low intensity.
Yeah. So now we're done through the feature extraction stage. Now let's look at the classifiers. So we use deep neural net based classifiers. So here's an overview of convolutional network. We have an image. We pass it through a number of two-dimensional filters. So we're doing a two-dimensional convolution, and followed by we do max pooling for dimension reduction. So the convolutional the convolutional operation and the max pooling operation together, we'll call them as conv 1. So we do another iteration of convolution followed by max pooling. We'll call them as conv 2. And finally, once we have some high some high level of features at the final stage or the pre-final stage, we pass them through a fully connected layer, which is and then the final stage we compute the softmax, do a softmax of the outputs to get the final predicted gesture. So we pretty much follow this architecture, except that we don't have this additional convolution. So we have conv layer 1, conv layer 2, followed by fully connected layer. So this is the first classifier that we built, straight vanilla CNN. So we also do a ReLU after doing convolution. So it has each conv layer has a convolution, ReLU, and max pooling. So input images. So these are the input images at every time instant. So these are of 17 by 17 dimension. The kernel width of these conv layer 1 is 2 by 2. So after some cross validation, we found that 3 by 3 or 4 by 4 doesn't perform very well. So, and the number of filters in each of the layer depends on the features that we're extracting. So for TOF we have 16 filters here and 32 filters here, and for intensity we have 16 and 16 in the layers. Max pooling is done over, so this is a dimension reduction part over an image of 2 by 2, and typically they're non-overlapping. And finally the output dimension of the fully connected layer is 128, and there's a softmax layer that transforms these 120 dimensions to the number of gestures that we have here, and we get the softmax output. So for a given utterance, which is a gesture start to a gesture end, we have let's say t images. Softmax output for t images. We take the mean of all the softmax output, as we are doing here, mean pooling over all images of a single sequence. So we get the mean softmax output and choose the max dimension of the softmax output. So that will give us the final gesture. So this is a typical scenario of sequence to multiple sequence to a single label classification. So this has depth in space, but it doesn't have depth in time. So to incorporate depth in time, we use CNN plus LSTM. So it pretty much the same network as earlier, except that after the fully connected layer, we have a LSTM block that models the temporal evolution of the gesture. So we use 128 memory cells in LSTM. And feed the output of the LSTM to the softmax, and as earlier we take the mean of the softmax outputs and do choose the max dimension of the after mean pooling. So this is both has depth in both space and time, and here we are passing an image at every instant. So let's look at the results of these two classifiers. Yes.
What is the size of the training set?
Oh, I'll be explaining that in the data set.
Because these usually need a lot of examples.
Yeah. We don't have.
Yeah, I would imagine that.
And I have another small question in the architecture. So do you use this to input the images in a FIFO fashion at the bottom, or after you use 3, do you use the next 3? Or do you shift them along?
So we pass the images sequence, but we typically do them in parallel operation. So we take 5 utterances and take the first, let's say 20 frames of all the 5 utterances and pass them as a batch, and then we take the next 20 of the same 5 utterances. So we make sure that we don't destroy the sequence information while training this. As opposed to in CNN, we can shuffle the frames and pass them to CNN, but here we input the images as a sequence. So data collection and evaluation parameters. So this is the 8-element microphone array and a single loudspeaker that I showed earlier, and this is the Mo2 A to D D to A converter and A to D converter that we use as an interface with our laptop, and on the laptop screen you see a GUI that are used to send commands to the device through the Mo2 interface. So this is the overall hardware setup, and now for the data collection. So data were collected for 40 subjects over 3 days in Studio B. Why Studio B? Because the HoloLens team is in Studio B, and they're very experienced with the HoloLens gestures. So we thought we can take their gestures, and each subject performed 5 gestures. So the gestures are tab gesture, which is just this one, the bloom gesture, the attention gesture, and the poke gesture, which is a horizontal moving finger, and the random gesture, which could be anything, any random gesture, but should not be any of these 4, exclusive from these 4 well-defined gestures. So each gesture was repeated 20 times. So each subject repeated each gesture 20 times. So 20 taps, 20 blooms, and so on. So the number of examples per subject were 100 examples. So the total number of examples, the total number of the size of the corpus is 40 subjects times 100, 4,000 gestures. So each subject spent about 25 to 30 minutes to give us 100 gestures. So in total we have we chose about 30 subjects gestures as training examples. We pruned some, so there are about 2,840 gestures as training examples, 500 as cross-validation set, and 400 as test set.
So the training set contains all subjects?
30 subjects only.
I didn't, only 30. Okay, I missed that.
So we made sure that an user who is in the training set is not a part of test or cross-validation. Yeah. Okay. So evaluation parameters. So to measure the accuracy of the gestures. So this is simply the classification accuracy. The true positives, the true negatives divided by the number of examples. So this typically means the number of classes, the number of times the true class, the predicted class agree with the true class, and then we also have a confusion matrix to analyze what kinds of gestures do get frequently confused with. So here are the experimental results of. So here are some ultrasonic images. So here's the first is a tap. You can see is it something like this? This is the index finger and probably a thumb finger, and this is the bloom. You can see so the white spots in the image is actually a strong presence of a strong signal, which is actually the shape of the object, and the dark bands are pretty much where we did not get any reflections from. So it's empty space. So in case of bloom, we can see that there's probably we can see 3 fingers, and these are the spaces between the 3 fingers. But we also get some reflections here. Not sure where they're coming from.
So in these images, are we looking at intensity then, not delay?
These are delay ones, the TOF features.
Okay, and then you just zeroed out the ones that have low intensity.
Yeah. And this is the attention gesture, which is just this. So you can see that. So this is pretty clear that this is just the index finger. Everything else is nothing around the object. And poke. I think the poke is actually the white horizontal band over here, where when the finger is moving like this. So this is the actual poke, but I'm still getting some echoes from in this in the vertical direction. I'm not sure why.
See the Doppler effects are represented in those images.
Yeah, I wish I could have computed the Doppler using the wideband cross ambiguity function, but here we are not capturing any Doppler spectrum. So, but I'm sure this will have the most significant this will have the most significant Doppler effect.
Now poke is parallel to the ray.
Oh yeah,
There's
that's
no
parallel.
Doppler shift.
There is no Doppler shift here. Yeah.
You may have Doppler here or here,
Yeah.
but mostly bloom actually.
Bloom, mostly bloom.
So in the tap, you said there should be 2 fingers that we should see in the picture, or is it 1 finger?
This one?
No, should there be 1 or 2 fingers that we should look for in the image?
So it's something like
2
this.
fingers?
Yeah. And here I'm going to play a video sequence for the tap gesture. So what's happening here is the user is the ultrasonic device is sending a beam. There is still nothing in the field of view, and the user gets his hand and does a gesture, and then takes his hand out of the field of view. So it's somewhere in between in this part of the video, in the middle part of the video, you'll probably see a tap, the two fingers touching each other. Okay. So I'll play this again. Yeah, this is how it looks like.
Can you show us where the tap actually occurred?
Yeah.
Fingers like this or like this? In the image, are they like this or like this?
So this was how the device was placed, and the users would go do like this and come back.
So the first line is the index finger, the vertical line. The white line, vertical white line.
This
is
one?
That, yeah, is that the index finger?
It's probably part of this part over here, and the index finger is slightly bent.
So the end should touch, basically.
These two regions should touch each other.
Can you play that again?
Yeah. I think in this room, Keith is the only one who has done. He was part of the subject also, right? I think. Yeah, subject. Yeah. So I'll try to. So something like this. Oh. Okay. So now for the results. So this is using the first using the delay features that we have, using both. We use the blue ones, the CNN, and the red ones. The orange one is with LSTM. So we have across different amounts of different number of classes, 5, 4, 3, and 2. So 5 classes. The 5 classes pretty much all classes. 4 classes is from tap, poke, attention, and none. So this should be actually tap, bloom, and poke, and attention. Tap, bloom, poke, attention. So none is not a part of this. So it's a typo. So 3 classes is tap, poke, and attention, and 2 classes just tap and attention. So you can see that using 5 classes, we get about somewhere around 52 to 54%, and we jump about 10% if we just get rid of the none class. We're actually just doing the four well-defined gestures, and among the 4 classes, we observe that bloom tends to get confused with tap. So if we remove bloom, so these are the 3 classes that we get, which is tap, poke, and attention. The recognition has jumped another pretty big, actually 15%. And then if we have simply tap and attention, we get about 97% accuracy. Yes.
So one question. So I don't use machine learning at all, so I'm not familiar with that. But I'm just wondering, and you're probably doing that with the non-class. How do you train for like everything else? Like, because obviously if you remove the non-class, then you jump a bit, assuming that you get only what you're looking for, right?
Mm-hmm.
Yeah.
How do you, like, in terms of, like, I'm switching hats here. If you were to deploy this, and maybe this is out of scope here, but possibly, I'm just curious about this. How would you then train for like this other class comprehensively so that you never, recognize a tap or something, or like a pinch for someone waving or something across the room? I don't know. Is that even or is that not hard at all?
So we can say that, so if you have the well-defined gestures, those features will be placed in some particular region in that n-dimensional space. But if you have a non, they'll be spread all over. So some of the features might overlap with the well-defined gestures. So it depends on how close these gestures are compared to the well-defined gestures that we can separate the features. So it pretty much depends on how well separated the features are for these. For the non-class.
The point is that none should be always presented, because you may have gesture 1 or gesture 2 or none of the above. and then you'll be able to distinguish just hand waving in front of the device from well-defined attention or click or bloom, etc., etc.
Yeah.
This is pretty much the point.
So, okay, so here's a look at the confusion matrix of the 5 classes over here. You can see that if you take the tap and the none class, so tap gets confused with none most of the times, and the none gets confused with tap most of the times. So if you remove this the none class, if you remove the none class, we can see that the tap has increased significantly. It just gets confused with bloom just once. So tap and none are the confusing classes, and here if you look at poke and attention, they tend to confuse among themselves more often than other classes. So there's interclass confusion between poke and attention and tap and none, and here we can see that here so here tap doesn't get confused with other classes, but bloom, similar to here, bloom gets highly confused with tap. Yeah.
You referred to before as random.
Yeah.
So and random was actually something in front of the camera, right? You didn't confirm it with none, actually nothing in front of the camera. How often do you actually trigger a gesture?
Yeah, it's just a naming convention. It's actually a random gesture. That's right. So
okay. In all of these, I think it would be really important to run this against true none. Like you run the sensor in front of nothing and see what your kind of false positive rate is.
Oh, okay, I see.
Right? Because otherwise you don't know like, how often does it trigger for nothing.
For nothing.
You do know that around 1/3 of the times, then you do something random, it triggers a tap, for example, from what I can see.
Right.
So.
And that's also dependent on what people did for that random.
Yeah.
I don't know what.
Which may be similar. Just simple waving can be considered as attention.
Yeah, I should have clearly mentioned that none is actually some gesture.
The problem is we can clearly distinguish when there is nothing in front of the device. That's not a problem. The problem is when the person waves their hand.
In the video, you said at the beginning you're seeing it nothing, then your finger comes in, you do it, and you move the finger away, right?
Mm-hmm.
I did not see that in the video at all. Like to me, it was like stationary. You're doing something maybe in.
No, I don't think there was nothing in the beginning. There was a finger right from the beginning.
Oh, maybe I misunderstood. So like there was no motion except this in the video. Or is the video contained like here's the frame, nothing is shown in there, you get in there, you click, you move away.
So yeah, it's the second one which you mentioned. So
this is what I'm like.
So it does pick up some.
What is the initial part of the content in the video? So when you go to the video,
okay.
When you begin it, so what is this?
Oh no, this is just an overview of the video. So.
Yeah, so in the initial part you see some white, right? So is that just noise?
So
next time we should connect the video camera and record in parallel what exactly happens visually.
Yeah, exactly.
Yeah.
That's a good idea. Mm-hmm. So is this showing empty scene right now, or is this showing the fingers already?
So this is here the finger is almost, it's in the field of view, but here let's say where's my mouse? Yeah, so there's some there's some image, there's some random noise.
Oh, so there are
so
no
this is
fingers
no
here.
hand in the image?
Nothing.
Yeah, there's actually nothing here at this point. Yeah.
Okay. Oh, that's a lot.
Yeah.
How big is your sensor array?
How?
Around 20 millimeters diameter. Is the circle where the
Just naively going from the diffraction limit, like you shouldn't be able to get this
The
resolution.
wavelength is 8 millimeters and this is less than 2 times the wavelength. Still, bats can go around wires which are 2 millimeters using the same wavelength. So theoretically, it's doable. How, we don't know.
So if it's showing image when there's nothing there, it seems like it's a thresholding problem. Maybe you need to bump the threshold up.
Yeah.
That leads me to a question I've been wanting to ask for a while is, in this ambient room, for example, like how much noise is there at this band? Like I've studied audio for a long time and I never thought about how much noise there is in these non-audible bands. Like, can you give a general idea, like, in this room, like how many ultrasonic noise sources are we currently not listening to?
So when you're collecting the data, actually, there was one, like we wasted a half day because there was, we figured that after collecting data from 10 users, there was actually an in-band noise right at 40 kilohertz. And it's even if I switched off all electronic devices in the room, and it turned out it could be, I believe, I suspect that it could be something. There was a nearby heavy electrical room in the neighbor, so it could be generating some kind of noise there. But in most of the cases, in the 40 case that I've showed here, there's almost nothing in the 36 to 44 kilohertz range. Yeah.
Do you think that would generate enough?
Yeah.
I think so. I don't know. I'm not an expert in audio, but I do feel like if you got some keys, most of the ultrasonic.
No, what he saw, I saw the recordings, was basically a steady tone at 40 kilohertz. It was, I don't, maybe inverter or something electrical, but because it was absolutely covering the band. Steady 40 kilohertz, constant tone. Quite actually loud. Some magnetostriction transformers vibrating at 40 kilohertz, and nobody even thought to measure it because
These guys also, the fluorescent lights also make some.
So in general, Keith, the point is very, very valid. Maybe we should just go and record to see what is there.
Isn't the beamforming, doesn't it collect some noise information that might also suppress some of this ambient noise?
In general, the beamforming is a spatial filter. It suppresses the noises coming from other directions than the lookup.
Okay.
So we go and do pixel by pixel post. It's just one chip for every frame. Post factum, you do estimate those 200 and something beams to get the value, the signal output for each point. So if there is a directional sound, or point sound somewhere, it will be suppressed based on the shape of the beam. But that's pretty much it.
Okay, so this is the delay features. Let's go ahead and look at some of the intensity features. So intensity features, we were doing much better in 5 classes by almost 10% improvement. However, for the 4 classes, it somehow went down. It's against our intuition, and 3+ for 3 classes pretty much the same range as the delay features, and for 2 classes we didn't go up till 95-96%, but we are around 87-88%. The confusions are same. The tab gets confused with none, and none gets confused with tab, and there are interconfusions between poke and attention also. So there is, you can see that based on this information, there is some complementary information that we can make use of from the intensity features, which is probably not present in the time of delay features, time of flight features. So conclusions.
Didn't you combine them?
So yeah, I'm going to talk about them in the future work, which is yeah,
There is one more slide is missing. Doppler features.
Yeah, Doppler feature. Oh yes.
This will resolve the bloom.
Yeah,
This will help you to disambiguate the bloom.
Yeah, it's true. So this is our first attempt at building a complete end-to-end ultrasonic-based gesture recognition prototype. We leverage the work from the previous 2 interns in this team. The features used were time of flight and intensity, and the images were 17 by 17 images. The gesture classification accuracy ranges from about 53.7 to 96.9%, and for intensity 63 to about 88%, based on the number of, depending on classes. So yes, the future work is, well, it's actually still in progress. I'm still running experiments on this. So we are trying to use, so this is like we have two CNNs this time. So the first CNN1 uses time of flight features, CNN2 uses intensity features, and we combine them here and then do a softmax and then do mean pooling. So I'm working on this to see if we can get improvement with 4 classes. So ideally we want to use our HoloLens gestures, which is tap, bloom, attention, and none. So these are the 4 classes we want to focus on. And we saw that 4 classes using delay and intensity features were roughly around the 63-64% range. We want to see if we can combine these 2 features and make it get better, at least 70%. Yeah.
One suggestion,
Yeah.
because when you work with image classification for images, which is not far from what you're doing, usually you use multi-channel images. You don't have one classifier for red and another classifier for green. You use multi-channel convolutional filters, and here what you have is one layer for one network for the time of flight, and another for intensity. So at least try the more common,
more the common architecture. So have
just multi-channel filters. The convolution layers, the first input layer actually accepts red, green, blue, or in your case, TOF and intensity per pixel.
And Doppler.
And Doppler, sorry, yes. So just because it seems to be working very well for the guys who do image recognition.
So I found that the 2D convolutional filter that I used for this and this are not the same. So if I use the same filter over both these, they don't perform this. One performs worse. So I thought just to have 2 different filters for each layer, for each kind of feature, and then do the and then do at the final high level representation rather than combining them at the lower level.
So you combine them across all levels. That's the whole point. You learn good features. Again, not sure, because red and green is different from time of flight and intensity
because
and Doppler. But you might try it, because this is at least seems to work very well for the other guys.
Sense.
I don't know. Maybe for your case this makes more sense. I'm just saying.
Yeah.
Worth trying. Also seems easier to me. I don't know. Yeah. Less coding.
So if I use the same filter in both the layers, so let's say if I use the filters here for this, the performance significantly goes down, and if I use this one over here, the performance
it learns from different
for different. Yeah. So probably when I'm
the whole idea is joint learning. So
yeah.
Clearly you can just move filters around. So.
Yeah. So maybe the localization, the local features that is learning through one through the channels is probably not the same. So yeah.
That by itself is probably quite interesting to know.
So yeah, I'm hoping that I'll be able to see some results by the end of this week. And here's acknowledgements. So thanks to Ivan and David Johnston and Shoaib for their guidance and patience in answering many questions. Zoncho and Difei for discussions. Tiantan for helping with CNTKs. So this is the first time I'm learning CNTK. And then Hackon for helping with data collection logistics in Studio B. And then all subjects for the patience in doing the gestures. And finally the MS Hardware team for giving us a hardware design early enough in the internship project. And overall it was a wonderful summer. And these are some of the references that I've cited earlier, and here's more details, and I'm open to questions. Yeah.
So, I like the discussion during the talk, but still if you have questions, remain unanswered. If not, let's thank again our speaker.
Thank you.
Thank you.